Hello guys, and welcome back to my organic chemistry video. So today we're going to be going over analytic reactions continued, and we are in the end game now, guys. This is like one of the final videos before the ACS, and I saw 14 million possibilities, and the most probable possibility was this being the actual last video. So with that being said, let's move on to analytic chemistry. So Aldol reactions. If you recall from the previous intro to analytes, analyte can look like this, or it can look something like this. Now then, for these Aldol reactions, you're going to want to utilize this form right here. And how these actually look is, since we have 2 times of the aldehyde in the solution, we can form an analyte, and we'll also just have a normal aldehyde present in that solution. And then via resonance, we can open up an electrophilic position on that aldehyde, which then can be attacked by the analyte, giving us our Aldol product. Sure, you count your carbons. I'll draw the new bond in red. And then the H actually is attached via that protic solvent, such as MEOH, ETOH, but we're not going to show that mechanism because I don't think it's going to be very helpful. But for the next example, same concept. Analyte forms. Then you also still have an aldehyde in the solution, which can then, via resonance, once again, open up that orbital. Let's do blue. Nucleophile can come in and attack that electrophile, giving you your product. New bond in red. And that's your Aldol product. Now then, Aldol reactions can also have something occur called Aldol condensation. This occurs when heat is present or when the OH is next to an adjacent benzene ring. So for the first example, we're going to look at the benzene ring. When this occurs, it's going to follow the same mechanism as a regular Aldol reaction. So once again, determine your electrophile and your nucleophile. For this one, it's a little bit trickier because this one you might think could form an analyte, but it actually can't because this position right here is not able to form an analyte. However, we can form an analyte here, and that's where we're going to want to form the analyte. So when that reacts with the ETO, you would get something that looks like this. This would act as your nucleophile, and then on the other side we just have our aldehyde attached to the benzene ring, and then once again, via resonance, we can resonate that up. Did not mean to do that. Sorry about that. You can resonate that up. Nucleophilic attack on that electrophilic position, giving you this product. New bond in red. pH, H from the ETOH. Now then, as I was just mentioning, if it's the OH is next to an adjacent pH or benzene ring, you can actually form the Aldol condensation product, which is going to be favored. And how that occurs is you have a hydrogen here that can donate its bond in, forming an alkene bond, and then the OH group can then leave, giving you the Aldol condensation product, which would look like this right here. And this is the favored product in this situation due to that adjacent pH ring. And I should mention, this product right here is formed a little bit in the solution. This is your Aldol product, and this is your condensation product. And this is the product we actually want. So let's look at another one of these, of how these actually occur. So this one might look a little bit more complex because I'm using some concepts from previous videos, but LDA, we know this forms an inlet in this case because it's going to cause a kinetic inlet to form. Because once again in the previous video, LDA forms the kinetic inlet. So that would look like this. Actually, see this? Thank you, Piplup, for your assistance. We don't form the inlet in this position right here because that would be the thermodynamic position. And since it is LDA, we want to form the kinetic position, which is highlighted in the yellow-blue region. So now then when we react this with an aldehyde, once again, open up that orbital. Then this can come in and attack, giving you this product right here. New bond in red. OH. Just like that. However, as you can see next to Charmander, there is heat involved. And when heat is involved, we can also form the Aldol condensation product. And some people get confused when we form the Aldol condensation product because they don't know what hydrogen to actually utilize to form the alkene bond. And a good tip to remember this is you want to utilize the hydrogen that would make a conjugated system with the oxygen. And what do I mean by that? So for example, say we formed the condensation product in this direction, going that way, and we ignored this hydrogen right here. We now don't have a conjugated system with the oxygen, meaning if we try to resonate this bond over, we can't resonate it onto that oxygen. So it's not in a conjugated system with the oxygen up here. However, if we utilized the other hydrogen, which is this hydrogen right here, and we have the OH group leave, and we have the hydrogen come down and then get grabbed by the base, which I guess I'll draw in real quick, we would then get product that looks like this. And then just so you guys don't get confused, I'll make it black again, which now does have resonance with this oxygen, meaning the negative charge can actually end up on the oxygen. And that's an easy way to remember what hydrogen to utilize. And this would be your favorite product, once again, the Aldol condensation product, due to the heat. So moving on, Claisen reactions. Let's first take a look at the saponification mechanism because I think it might help you guys understand these a little better. So if you recall from the previous subject matter we covered in Orgo 2, you'd remember that the saponification mechanism occurs when NaOH is present with an ester. And how that looks is like this. So the first step is something that looks like this. However, we can then resonate this negative charge down, kick out the ester group, giving us the step 2. Well, these aren't really steps, these all happen instantly, but for our case, we'll put them in steps. Which would then give us something that looks like this. And then you have to recall, we still have some of that present, and actually I forgot this looks like that, my bad. since it was kicked out, we still have some of that present. This can then donate into the oxygen. This can grab the hydrogen, giving you your final product, which would then look like this right here. Hydrogen attached to that, my bad. Which would look like that. And that's the saponification mechanism. And the Claisen reactions actually basically follow this mechanism. However, I found an easier way to do them, which is the way I'm going to show you. So now actually looking at the Claisen reactions. The simplest way to do these is to determine your nucleophile and your electrophile. Now the ester is always going to act as the electrophile in your Claisen reactions. And the ketone / aldehyde is always going to act as the nucleophile. So first step is determining where the inlet is going to form. Is it going to form here or is it going to form here? Now the Claisen reactions actually prefer the kinetic product. We'll just say kinetic inlet, meaning they prefer the less stable position than the less sterically hindered position. So that would be this position right here. So then your inlet would actually look like this right here. And that's the inlet we're going to utilize in order to attack the electrophile, which is going to be your ester. And how this then occurs is go back to your ester. Let's get rid of this guy right here. Let's move him up. Your ester would then, this isn't the actual mechanism, but this is the easiest way to think of it, act as a leaving group. This can come in and attack, giving you a product that looks like this right here. New bond in red. Looks like that. And then of course, it usually would have a negative charge right there. However, the ACS does not show this negative charge, so for our case, we're just going to ignore it. Next example, if you have 2 times of the ester present, it can do the same thing. And it basically follows the same mechanism. The only thing that's a little different is you're going to have an ester attached on the end product. So how this looks is, once again, an inlet would form on one of the esters, which would form right there. We would then have another ester present in the solution. Right here, which once again can act as a leaving group, opening up this orbital right here in order for the nucleophile to come in and attack, giving you a product that looks like this. New bond in red. And that would be your product for this reaction. So not a very hard reaction. Now one thing I should note is if NaOH is present, tread very carefully, because if you remember, NaOH does a saponification mechanism, which would then leave this looking like this. If we did end up utilizing NaOH, you would get one that looks like this. So, and that's not how these reactions occur. We don't want to use that. So NaOH is never utilized for Claisen reactions because they will form the saponification product. So moving on, cyclization. These are pretty basic. If you recall from the previous material, a cyclization is just basically an intermolecular cyclization, exactly like it says. And the 5 and 6 member rings are the most stable and are what are preferred to form. So how these actually occur is, once again, figure out where the inlet's going to form. Is it going to form here, 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 or here? And what you have to know is that we want a 5 or 6 membered ring. So if we count from here, 1, 2, 3, 4, 5, 6, that's a preferred inlet. If we count from one of these inner carbons to form the inlet at, 1, 2, 3, 4, that would give us a 4-membered ring, which is not favored. So we're going to use one of the outside carbons to form our inlet. And it doesn't matter which one we actually choose because it is a symmetrical molecule. So let's say we use this one, so the inlet forms here. Then all you have to think is count 1, 2, 3, 4, 5, and then 6. This would resonate up. Nucleophilic attack. Draw in a 6-membered ring. At the 1 position. So number your ring if you want to, which I would do. The 1 position we have nothing. At the 2 position we have a ketone. At the 3rd position nothing. 4th position nothing. 5th position nothing. 6th position we'd actually get an OH, and we would also have a methyl. Now then tell me what's unique about this. I'll give you a second. If you figured that we have heat, so the aldol condensation product is going to form, you're 100% correct. So that would then mean that there's a hydrogen here, the OH group would get kicked out, hydrogen would come down, forming that alkene bond, giving you your final product, the preferred product, which would then look like this right here. So, next one is also a cyclization. Occurs a little differently though. Once again, figure out where your inlet's going to form. We have 2 positions it can actually form, here or here. So it's symmetrical, so it doesn't really matter where it's going to form at. So just count 1, 2, 3, 4. We really don't want to form that because it is a 4-membered ring. However, it can occur with these reactions. It wouldn't be preferred. However, if you are only given this option on the exam, there are some in the ACS where it will give you a 4-membered ring, and they are all 4-membered rings, and you just kind of have to figure out how it's going to form. It's not preferred, however, they can sometimes form it. It's a little weird of a concept when you actually have these molecules that actually have esters attached. And how they actually work is form your inlet, which is right there. Resonate up. This actually then gets kicked out. Comes in, attacks. This then actually resonates back down, giving you the product, which is 1, 2, 3, 4. So then number your 4-membered ring, which once again is not preferred. However, if you are given a problem that is wanting you to cyclize, they can do it. It's just not recommended. 1 position we have two position nothing, 3 position nothing, and then the 4th position we would actually have that, since the OET actually leaves. So, I hope that makes sense. Once again, don't really want the 4-member ring to form, but there are some examples in the ACS where you don't have a choice. They want you to form the 4-membered ring. And it'll never happen on something like this, but if there are esters involved, it can happen. So here's another cyclization problem, a little bit more complex of one. When we react this with NaOH, of course, the first step is going to be an inlet that forms Now, would we want to form it here or here? Well, I hope you know we physically can't form it here because there are no hydrogens available. So it would have to form on that outside carbon. Once again, 2, 4, 6, 8, that means there's 4 carbons and it is neutral, so there are no hydrogens. Now when we react it with this molecule right here, you might get a little confused. However, just remember back to your basics and know that this can resonate like that, opening up the orbital. This can then come in and attack. It's going to look like a really nasty product. Looks like this. Negative charge there. Now the ACS is not going to show the negative charge, so we're not going to put the negative charge there. They'll actually have a hydrogen come back and attack, because I think they actually utilize H3O plus, so a hydrogen can't come back and fill that negative charge in. And then we have the new bond form. And once the new bond forms, you would get a product that looks like this. I know it looks kind of nasty. And now that we react this with NaOH and H3O plus, that's another saponification, another inlet formation. So then we can determine where our inlet's going to form. Is it going to form here, 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 not there? Oh yeah, here, or here. And once again, since we can't form it there, we can knock that one off. And now it's going to come down to what ring would be more stable. So if we count from here, if we form the inlet here, 1, 2, 3, 4. That's not where we want to form that, because we don't want a 4-membered ring if we can make a better ring. If we go here, 1, 2, 3, 4, 5, and then 6, that is a preferred ring. So that's the one we're going to take. We're going to take this position right here in order to perform the cyclization. So then form your inlet. This would resonate up, come in, attack, draw a 6-membered ring out. Once again, this is a complex problem, so number your ring. 1, 2, 3, 4, 5, and then 6. The 1 position we have nothing. At the 2 position we have our ketone. 3rd position we have nothing. 4th position we have that. 5th position we have nothing. 6th position we actually would get an OH, and then this crazy looking thing. Let me make sure I count my carbons properly. 1, 2, 3, 1, 2, 3. Erase 1 carbon. Always count your carbons. And then we can actually do an aldol condensation because we do have heat present. So the hydrogen can come down, the OH can leave, giving us our overall product, which would look like this. Once again, always count your carbons. And that would be your overall product. Looks kind of crazy. I know this is as complex as they're going to get for cyclizations, though. moving on to the practice with inlets. So now we're just going to go over a bunch of different inlet reactions, and I'm going to explain how they occur. So we have two esters prevalent. One of them is going to have to form an inlet, and one of them is going to have to act as the electrophile. You tell me which one's going to act as the electrophile and the nucleophile. I'll give you a second. Well, we know this is going to have to act as the electrophile, and this is going to have to act as our nucleophile, because we physically can't form an inlet with this one. There's no part of this molecule that can form an inlet. I mean, you could technically form one here on that benzene ring, but it's way too sterically encumbered to actually occur. So you're never going to form an inlet on the pH or the benzene ring. So with that being said, the inlet would form here. That would leave this open. It's an orbital because, once again, that ester can act as a leaving group. This can come in, attack that open orbital. Giving you a product that looks new bond in red, like this. So, not too hard, not too hard. The next one is pretty easy to figure out. You have two aldehydes in a reaction with NaOH and H2O and heat. So we know that an aldol condensation product is going to form because of that heat. So first, let's just figure out the aldol product. Inlet forms, then it would attack another one of itself. Let's draw out the aldol product in blue. New bond in red. Giving you something that looks like this. However, since heat is prevalent, we can form the aldol condensation product. This can get kicked out, giving you your overall product, which would look like this. Count your carbons once again just to make sure. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then make sure you form that conjugated system with the oxygen when you form your condensation product. Moving on to the next example. NO2 can also form inlets, which I've actually never gone over, but it follows the exact same mechanism. So your inlet would form here. You would then want to resonate up, opening up this orbital, making this negatively charged. Inlet can then come in, attack there, draw the product in blue, red bond to the new product. Once again, always count your carbons just to make sure. We want to have 1, 2, 3, 1, 2, 3, 1, 2, 1, 2. And that is your aldol product, and we would not form an aldol condensation product with this because, once again, there's no adjacent benzene ring and there is no heat present. So, continuing on with this, shouldn't be there. We now have NaOET and ETOH. and we have a benzene ring right here. So once again, form your analyte, act as a nucleophile, resonate upwards. I don't even know what that is. Nucleophile can come in and attack. New bond in red. Just like that. Now then, we do have an adjacent pH ring that can form. So you would then form the Aldol condensation product, giving you an overall product that looks like this. And that's the final video, guys. Thank you so much for watching. I hope you guys have successful future endeavors, and I'm glad that I could assist you guys on your organic chemistry adventure. Until our paths cross again, that's all, folks.